In the previous lesson, we learned that when you're talking about a current carrying wire and you were to place it inside a magnetic field, that wire will experience a magnetic force, which you can actually predict using Fleming's left-hand rule. So for the next part of our lesson, we are also still going to be talking about a wire right now, but specifically we are going to look at two parallel wires, right? Hence, we are looking at parallel current carrying wires now. Now, for the case of parallel current carrying wires, the wires will also experience a magnetic force because one wire is actually inside the magnetic field of the other wire. If you have the wires having current in the same direction, the nature of the magnetic force will be attractive. But if on the other hand, the wires are carrying current in the opposite direction, the nature of the magnetic force experienced by the wires is that they are repulsive. Now, why are the forces attractive and repulsive here in the first place? You can actually analyze the wires one by one. So this one, you just have a look at the next page. Just now I was mentioned to you that when current flow is in the same direction, the wires will experience attractive forces. So let's just consider two wires now, wire 1 and wire 2. Now let's just consider wire 2 alone first. When wire 2 has current that is flowing in this specified direction, current I2 now, you learned in the previous lesson that any current that flows through a wire will produce its own magnetic field. And the nature of that magnetic field is that it's in the form of concentric circles. So if you were to just draw in 2D, the magnetic field in 2D, you will actually just see the magnetic field as a series of circles with either crosses and dots. So for the magnetic field with crosses, that magnetic field is actually into the plane of the page. But for the magnetic field with dots here, this is actually telling you that the magnetic field is out of the plane of the page. Okay, the directions of the magnetic field here, you can actually predict using your right-hand grip rule. Okay, so now for wire 2, you now have a magnetic field that is established when current flows through it. This side is magnetic field into the plane of the page. This side is magnetic field out of the plane of the page. Now, for your case right now, there is another wire. Your other wire is wire 1. Okay, wire 1 is now inside the magnetic field of wire 2. This part here you notice is having a magnetic field, is coming out of the plane of the page, but it is the magnetic field that is caused by wire 2 itself. All right, so right now wire 1 is inside the magnetic field that is caused by wire 2, and at the same time there's actually current flow through wire 1. So there is a magnetic field, there's current flow, there is supposed to be a magnetic force that is going to be exerted here, which can be predicted using Fleming's left-hand rule. If you recall Fleming's left-hand rule tells you that your thumb should represent your magnetic force, your index finger should represent your magnetic field, and then your middle finger should represent your current. So if you apply Fleming's left-hand rule to this portion of your wire right now, you consider the direction of the magnetic force, you consider the direction of the current, eventually you will be able to find out that the magnetic force is actually pointing towards the right for wire 1 itself. Okay, so the magnetic force that is exerted on wire 1 is actually due to the fact that wire 1 is inside the magnetic field of wire 2. Okay, so we already predict the direction of the magnetic force on wire 1 itself. Now, you may be wondering, if now there's a current flowing through wire 1, shouldn't it also establish its own magnetic field? By right, yes. Because now there's also a current flowing through wire 1 itself, it also establishes its own magnetic field, which is represented by this series of circles with crosses and dots here. So this portion here is where your magnetic field is coming out of the plane of the page. This one is magnetic field going to the plane of the page. This is specifically the magnetic field caused by wire 1. Okay, and now you can actually apply a similar analysis. If you look at this part itself, wire 2 is now inside the magnetic field caused by wire 1. You have a magnetic field coming in, you have a magnetic field going to the plane of the page. You have a current direction that is going upwards. So by right, you're going to have a magnetic force too. So if you were to then apply Fleming's left-hand rule for the second wire, you would then be able to say that the magnetic force will be going towards the left for wire 2 itself. That's why here, when you have current flow in the same direction, the forces are going to be attractive. Because if you were to individually analyze the wires, you can actually predict out the direction of the magnetic force. But there's a way to work around that. You don't really need to like analyze each individual wire. There's a shortcut to it where you just analyze one wire. If you were to just analyze one wire, the first wire that we analyzed just now was wire 1. We went through the whole process of applying Fleming's left-hand rule there, and we found out that the magnetic force is acting towards the right. Okay. Now, from here, what we can then also say is that the reason why wire 1 experienced a magnetic force was because it was interacting with wire 2. So from Newton's third law mentions that when two bodies interact, they tend to exert equal opposite forces on each other. So wire 1 right now experiences a magnetic force F1 due to its interaction with wire 2. So by right, wire 2 must experience an equal opposite force. So your F2 will be in this direction, which is the same direction as what you would get if you were to analyze wire 2 individually just now. Okay, so this is actually the shortcut to it. Now you can do a similar analysis when the currents are flowing in the opposite direction. Either you analyze the wires individually, or either you analyze this wire and then apply Newton's third law. If you do either one, you will eventually find out that your magnetic forces will be pointing in this specific direction, telling you that the forces are going to be repulsive. Okay, so that's how you predict the direction of the magnetic force on parallel wires. So for the rest of the notes here, it's actually just a rehash of what I just mentioned. We'll go through the points one by one. So as current flows through each wire, they produce their own magnetic field, which are concentric circles that spread out from the center of the wire. Each wire is in the magnetic field of the other wire, meaning to say wire 1 is in the magnetic field of wire 2, and similarly, wire 2 is in the magnetic field of wire 1. If we had just considered wire 1, since current is flowing through it and is perpendicular to the magnetic field formed by wire 2, a magnetic force would thus be exerted on wire 1, which we predicted using Fleming's left-hand rule. And then as for the magnetic force on wire 2, rather than analyzing it individually, we can actually just say that an equal opposite force should be exerted on it according to Newton's third law. All right. And one last thing to note is that when it comes to the current flow in the parallel wires, the current in both wires may be different, but the magnitude of the forces experienced by both wires ought to be the same. This is actually quite similar when you're talking about gravitational force. Okay, if let's say you have a person here and then you have Earth here, Earth has a mass of maybe 6 times 10 power 24 kg, whereas you may have a mass of say 60 kg. So what you learned under the gravitational field chapter was that you have these two different masses. By right, there should be gravitational forces exerted on them, and they will be equal opposite to each other because of Newton's third law. So in my case, if I were to take G as 10 meter per second squared to make my calculation simple, this one would have been 600 Newton for the gravitational force on the person. But as for the gravitational force on the Earth itself, it should also be 600 Newton. Okay, so notice here that even though your masses are different, the forces experienced would be the same. So it's something similar here when you're talking about the forces acting on the parallel wires. Your current magnitude can be different, but the forces that arise as a result of that will still be the same because of Newton's third law. All right. Okay, then after that, if you move on to the next page, there's this point here where we mentioned that for current that is in the same direction, there is a neutral point between the wires where the magnetic fields are going to be equal in magnitude and opposite in direction, so that the resultant field is 0. Okay, so what do we mean by that? This one you have to look at for the case where current is in the same direction. So for the case where current is in the same direction, it actually refers to the first diagram that you have over here. So notice that the magnetic field for this region here that I just indicated using the green box, the magnetic field is actually acting in opposite directions. The magnetic field of wire 2 is coming out of the plane of the page, whereas the magnetic field of wire 1 is going into the plane of the page. So they are acting in opposite directions here. All right, so you notice that this and this, they are acting in opposite direction. So because they're acting in opposite directions and they're combining together, there will come a point where the magnetic fields due to each wire are equal and opposite, and they cancel each other off. So where they cancel each other off, that is where you will consider that as your neutral point, where your B is equals to 0. Your resultant magnetic field is 0. Okay, resultant magnetic field is 0. Okay, that's what that point actually meant. Now, for the case just now where I mentioned that when currents are acting in opposite direction, for the cases that I mentioned when the currents have different magnitude, the magnitude of the force experienced is the same, other than referring to Newton's third law to explain why they are going to be the same, you can actually also prove it by equation, okay? The proving by equation one is actually not so common because it's a bit tedious, but I'll just show you anyway because your exam question sometimes refers to this answer here. All right, so let me just draw for you a simple and diagram that shows you two parallel wires. Maybe we consider the magnetic, maybe we consider that the current that acts on each wire is in the same direction. Okay, so I call this wire 1, and then I call this wire 2. So the magnetic field that is caused by wire 2, it will be in the form of concentric circles like this. So if I use right-hand grip rule, I will say that the magnetic field will be coming out of the plane of the page over this side and going into the plane of the page over at this side. All right. So right now, I want to analyze the magnitude of the magnetic force acting on wire 1. Just now, we already said that the direction of your magnetic force on wire 1 is going to be in this direction, isn't it? By using Fleming's left-hand rule to predict the direction. So right now, I want to calculate out the magnitude of this magnetic force. Let's call this FP1, right? So one thing to note is that when you're talking about current carrying wire or current carrying conductor, the magnetic flux density B at the distance D from a wire carrying a current I is actually given by this equation. B is equals to mu naught I over 2 pi D, where mu naught is some sort of constant called the permeability of free space or vacuum. All right. So what this means is something like this. If your wire is something like that with a current I, if you're talking about distance D from the center of the wire or from the current itself, B equals to mu naught I over 2 pi D gives you the magnetic flux density at that point, at that particular distance D from the center of the wire. Okay, I here is your current, D here is the distance from the center of your wire, and then 2 pi is obviously a constant, mu naught is also a constant. But for your analysis, we simplify those constants as just K, all right? We assume that mu naught over 2 pi is just K for the derivation below. So right now, the magnetic force that is acting on wire 1, if you recall what we learned in the last lesson, we learned that magnetic force on a wire perpendicular to a B field or magnetic field is actually FB equals to BIL. And then this one, this B that you're talking about is the flux density of the B field that the wire is in. Okay, that the wire is in. Just let me rewrite this properly. Okay, the B that you're referring to is the flux density of the B field that the wire is in. Then how about the current I that you have in the equation? This current I that you have in your equation here is the current in the wire itself. Okay, because you're trying to find out the magnetic force acting on a particular wire, that current that you have here is actually the current inside that wire itself. Okay, and then after that, the other one, this L here is the length of wire inside the magnetic field. Okay, so right now, if I wanted to find out the magnetic force acting on wire 1 right now, FB1, it will actually just be equals to B2 I1 times L. Why is it B2? It's because you are inside the magnetic field caused by wire 2. Why is it I1? It's because you're considering the magnetic force on wire 1. So you are going to consider the current through wire 1 itself. So it's B2 I1L here. Okay, so that is for this part here. Now, if you then want to consider the magnetic force acting on wire 2, this one we make our analysis simpler. We know that according to Newton's third law, the magnetic force should be equal opposite to that of wire 1. So we can actually just straight away say that in my case, the magnetic force on wire 2 is actually going to be in the opposite direction. But what I'm interested now is the magnitude of the magnetic force here. So wire 2 is inside the magnetic field of wire 1. So let me just redraw out the diagram with the magnetic field indicated. So if you're talking about wire 1, it produces its own magnetic field, where in my case, the left part would be having magnetic field coming out of the plane of the page, whereas on the right part, the magnetic field will go into the plane of the page. Okay, so right now, if I wanted to find out the magnetic force on wire 2, it by right should be B1 I2 times L. Why is it B1? It's because it is in the magnetic field of wire 1. Why is it I2? It's because you're talking about wire 2 right now. You have to consider the current in wire 2. Okay, so these are the expressions for the magnetic forces on wire 1 and wire 2. So right now, if you look at the workings that are already written inside the notes, I wrote for you that wire 1 is F1 equals to B2I1L. For wire 2 is F2B1I2L. So remember just now I told you that your B for a wire carrying a current is generally given by this. So you want to expand out the B according to the respective wires. In your case, this one, B2 will be KI2 over D times I1L. And then the other one will be KI1 over D times I2L. Okay, so B2 is based on this equation. B1 is also based on this equation here. All right. The mu naught over 2 pi, I've already simplified it to K, just to make the equation look a lot simpler. So at the end of it, if you try to explain out equation 1 and 2, you will notice that F1 is actually equals to F2 is equals to KL over D times I1 times I2. The equations are actually the same. Therefore, I can actually say that both forces have the same magnitude, although the current are different. Okay, the magnitude is actually directly proportional to the products of the current. Okay, so this is actually a more long-winded way of proving that the magnitude of the magnetic force are going to be equal, even when the currents are different values. Okay, it will be much easier to just to explain it using Newton's third law. Okay, so let's just do some questions from there.